Okay, so today we're going to be looking at applying differentiation strategies so that we can sketch derivatives. Now, this is one of the best things that we can learn how to do with our derivatives because you would have noticed in the past we have a problem when we're trying to work out the maximum, the minimum points of things like cubics, quartics, quintics, and as it goes up in polynomials, it becomes harder and harder to determine where those maximums and minimums are. Now, you can kind of estimate them by chucking in values and trying to get closer and closer to the maximum point until it starts to go back down to a minimum point. But there is an easier way to do it, and it's with using derivatives. Now, over the last couple of lessons, we've been really trying to hammer down our language of derivatives. So I've been emphasizing to you what a stationary point is and what a point of inflection is. So a stationary point is when our first derivative is equal to 0. So the stationary point here, first derivative equals to 0, and that's going to tell you the x-coordinate of where that maximum or that minimum occurs. Okay, it's also, more technically, where the gradient of these functions is equal to 0. So this is a stationary point, that's a stationary point. Now, this is different to a point of inflection, which is when the second derivative is equal to 0. Now, this point of inflection tells us about the concavity of it. So here, if I have a function that looks like that, you can see here it's approaching the max, and then as I get over, it starts decreasing. But this point here where it changes from approaching the max to approaching the min, that switch over, that is the point of inflection. So that is what we're looking for when we're talking about determine the point of inflection. Now, when we're determining the nature of stationary points, that means we're going to test around the stationary point to see what its gradient is doing. Okay, when I take the first derivative of something, I'm really just looking for a beautiful story about the gradient of that function. So if I'm testing the nature of the stationary point, it means I'm testing around that function to see what the gradient's doing. So nature, testing. So once I've determined where my stationary point is, if I test something on this side, and it gives me that the gradient is positive. And then if I test something on this side and it looks like it's going down like that, or the gradient's a negative, then that would mean that it is approaching a max. If I test the stationary point around it and I find that it's doing the opposite, so it's decreasing and then increasing, then I found that it's going to a minimum point. Now, there is one other type of point that we can talk about, and it is a stationary point of inflection. Now, to be a stationary point of inflection, that means you have to have your first derivative equal to 0 and you need your second derivative to equal 0. If both of those statements are satisfied, then it means that you are both having a gradient of 0 and you are changing your concavity. So that means that you could look like this, where that's your gradient there. So the gradient there is 0. It's changed from approaching a minimum to a maximum at that point. So that's an instant of stationary point of inflection. The other way it can look is like this. That's another one. So gradient is 0, it's changing concavity. So if you can really, in your mind, understand these terms, it'll make the next year a lot easier because this stuff comes up a lot. Okay, so the other thing that we're going to do in this question is we're going to determine the concavity of the stationary points. Now, this is easy because we remember happy faces and sad faces. So this one here, you can see that as it's approaching the maximum value, it looks like a sad face. So anywhere between this point and this point, our gradient is going to return to us a negative value. And over here, you can see this one looks like a happy face. So anywhere between this point all the way over to here, it will return to us a positive value. So we're testing around the stationary point, around the point of inflection to see what the concavity of this stationary point is. Okay, so let's look at this through a worked example. We're going to start off with this part here. So y equals x cubed plus 2x to the power of 4 plus 3. Let me just check Desmos. I'm going to change that one to a 2. That's better. Okay, so determine the stationary points. That means I'm going to calculate the first derivative of this function, which means I'm going to derive our function with respect to x. Which means that the first derivative of this function is going to be 3x squared plus 4x. This last 3 has got no x's to give, so he just goes away. Okay, now the next thing I'm going to do to determine the stationary point is let the first derivative equal 0. So this is going to require us to use factorizing. Now, a lot of the time, if we're looking at a cubic, this is going to turn into a quadratic. So, like I said, quadratics are everywhere. If you still don't know how to do them, make your life easier by going and looking it up and practicing every now and again. Okay, so from here, I can see I've got an x there and an x there, so I'm going to factorize an x out. X, and then inside I've got 3x plus 4. Now I can let null factor rule apply here to work out our first stationary points. So the first one is going to be x equals 0, because I let this part equal 0. And then I'll let the next bracket equal 0. And I'm going to rearrange to solve for x. So these two, when x is 0 and x is negative 4 on 3, they are the points where a stationary point lies. Now, it doesn't tell me anything about where it's located, other than if this is my number line, there's a stationary point somewhere along here, and over here at negative 4 on 3, there's another stationary point somewhere on there. So that's what we've actually found over here. If it was asking me to find the max or the min, well, I found the location of the maximum and the minimum, so I can put these values back into my original function to find out where they are. That's not what it's asking us. Okay, the next point is actually determine the stationary points. So I do need to substitute them back in to find the coordinates. So let's do that now. So we're going to let x equals 0 in our original function. So y equals 0 cubed plus 2 times 0 squared plus 3. Therefore, y equals 3. So our first coordinate is when x equals 0, y equals 3. The next one, we're going to let x equal negative 4 on 3. Okay, so now we're going to substitute this value into our original function. So this is how I'm going to show that I'm substituting this value back into this function here. So there we go, negative 4 on 3 plus 2 times negative 4 on 3. Now that's squared, that's cubed, that's plus 3. So that's going to give me 113 over 27, or about 4.185. Okay, so what we found is they are the coordinates of where this thing happens. So if I quickly just draw a little sketch over here. Okay, I've got negative 4 on 3. Obviously, this isn't to scale. I've got 0 there. And I know that I've got an intercept here at 3. And there's 1 up here at 4.185. So here is our first coordinate. Here is our next coordinate. So looking at that drawing, we can already determine that this is going to be going to a max and then down to a min. But we're going to prove this by testing the nature of it as well. Okay, so that's part A. Part B is to determine the point of inflection. So that means we're going to let the second derivative equal 0. So I'm going to take the second derivative of our other function there. That's going to become 6x plus 4 is equal to 0. Move the 4 across. So then x is equal to negative 2 on 3 once you simplify it. Now I'm going to chuck that into the calculator. And that's going to give me, so when I substitute this back into our original function, that's going to give me 97 over 27. So I've taken this number here and I've put it back into this one to figure out the coordinate of it. Now if I convert that to a decimal, it's 3.59. So on my little number line, that value will be about here, minus 2 over 3. And then it's just in between these two here, probably about there. So this is the point where it changes concavity. So from this point so far, anything above here is going to return to me something to indicate that we're doing maximum things, and down here will indicate to me that we're doing minimum things. So if I'm testing the nature, I should find either side of the stationary point. This one's going to be positive and then negative, and then this one over here will be positive. If I was testing using the secondary thing to do concavity, then anywhere in this section is going to return to me a negative value because it's a sad face. Down here it will return to me a positive value because it's a happy face. Okay, so now I'm going to show you how we state all that information to test the nature of the stationary point. So we're going to start by doing up a little table here. So this is C. Testing nature. Okay, so to test the nature of our stationary point, I'm going to state the stationary points first. Now, we determined that the stationary point, we just want the x coordinate of it. So stationary point exists at negative 4 on 3 and 0. So we're going to take these two values and we're going to pick values either side of it. So here I'm going to have the x component. Here I'm going to have the x dash component. And I'm going to leave 1 this side of it. I'm going to pick this value. I'm going to pick 1 that side of it. And then I'm going to have 0. Okay, and then I'm going to pick another one on this side. So I'm really going to substitute 3 things into our first derivative. Now, if these are stationary points, that's where our derivative is equal to 0. Now, I'm going to add in an extra thing so we can talk about the slope at the same time. So, pretend that line's straight. Slope looks like that, the slope looks like that because it's at 0. You can pick any value you want. So down here, I'm going to pick negative 2. I'm going to pick in here negative 1, and I'm going to pick over here positive 1. Now the reason why I've chosen these values is because I'd prefer to work with whole numbers, but this is a number in between this number and this number. And this one is just larger than this one, and this one is just smaller than that one. So I'm picking one value either side. So if I substitute this into our first derivative, so just to remind you what our first derivative was, it's when we've got 3x squared plus 4x. So if I substitute in negative 2, I'm going to have 3 times negative 2 squared plus 4 times negative 2. So negative 2 times negative 2 will make positive 4, times 3 will make 12, plus negative 8 will give me positive 4. Now, I don't care what this number is. The only thing that I care about is it's positive. So if this is a positive value, it means that your slope is going up. It's increasing. So your slope is positive. That's all I'm taking from this. This could be a huge number. It could be a tiny number. As long as it's positive, it's telling me about the slope. So next one, if I substitute in negative 1, now I'm not going to do all the working again. We're just going to talk it through. So negative 1 squared will make positive 1 times 3. We'll just make 3 plus negative 4 will make negative 1. So at negative 1, I get negative 1. Now, so I don't care about what the 1 is. I care about the symbol in front. So this is negative, meaning that your slope will go down. Now, over here, for this one, when I substitute in positive 1, I'll end up with 3 plus 4. It'll be 7. So here it's 7, but it's positive 7, meaning that your slope will go up. So if I'm then going to state what's happening or testing the nature at these points, if I think about this as a graph, it's going to look like that, meaning that this must be a maximum and this must be a minimum. So therefore, x equals -4 on 3 is max, and x equals 0 is min. So when it's testing the nature, that's what we are going to say is our final statement. Okay, that's all I really wanted to find from that. So the next thing we're going to do is I'm going to prove the same thing. I'm just going to show you how to do it if it asks you to test concavity or to use the second derivative test. If it doesn't tell you explicitly which one to use, you can pick whichever one that you want to use. Testing concavity. So we're going to start with the same thing that we did before. We're going to start with a little table. So we're going to have x. And then we're going to have our second derivative. Now I'm going to choose where our second derivative was equal to 0, which was -2 on 3. So at -2 on 3, it was 0. Now I'm going to pick a value either side of that -2 on 3. So that's going to let me test either side to see what's happening to the concavity. Okay, so a value slightly less is going to be -1. A value slightly more is going to be 0. Our second derivative was equal to 6x plus 4, meaning that if it's -4, then this is going to be -2, meaning that it's a sad face. This is going to be the changeover spot. Nothing happens there. It just helps me determine what's happening either side. If I substitute in 0, then it's going to be +4. Again, I don't care about this number. I care about the symbol. So because it's positive, it makes a happy face. So it would have been better if it was the other way around, so I could say, like, you're sad, so it's a downer. They don't think about this, stupid science people. Okay, so it's going to look like magic because I've drawn these little things, but I always forget which way concave up and concave down are. So concave up is when it's going peaking like this. It's also referred to as convex. Now, concave down can also just be referred to as concaved. So that's the one that makes a little happy face. So here, I can say over here, therefore, when x is less than little one eats the big one, 2 on 3, convex, and when x is larger than that, concave. Okay, so there we go. We've tested concavity. Good job.